Hi everyone, welcome back. My name is Ananth, and today we're going to be talking about asymptomatic efficiency. So asymptomatic efficiency refers to how we can describe the performance of an algorithm with respect to its input size as its input size grows. And we take two major perspectives on this, one being from runtime and the other being from space, where space just refers to the memory. The reason for using asymptomatic efficiency is it's actually a very good strategy in identifying memory and performance bottlenecks in an algorithm early on, which becomes very useful when scaling an application. Next, it also allows us to measure two different algorithms irrespective of the hardware used, making it a fair and just comparison. Our main technique for measuring asymptomatic efficiency is something called big O notation, where with respect to the input size, we measure the upper bound of an algorithm, or how fast or how much memory it'll use in the worst case scenario. And to do this, we may measure major factors and usually ignore smaller constants. So in the following code, we have a for loop, and the way to measure its time complexity with respect to n is to measure how many times the for loop runs. So in this case, it's pretty straightforward. We're going through the for loop, iterating n times, and within the for loop, we're just printing out the index, which is a constant operation, and this comes out to be big O of n. Next, for some more practice, we have the same example as before, where we're printing the indices of the for loop, but now we have nested it. So because we have a for loop on the outside running n times, where each time an iteration of the outer for loop occurs, we run again n times on the inner for loop. This comes out to n times n, leading us to have O of n squared. Finally, for the following code, we have a method that accepts an int array and an integer value target, returning true if the target is inside the array and false otherwise. And the way we go about determining the time complexity of something like this, it's first always helpful to revisit our definition, where asymptomatic efficiency refers to the performance of an algorithm with respect to its input size. So in this case, the inputs are target and R, where target is always going to be just one value, so we can call that constant. And the array is going to be a variable length. So we don't know what the user is going to put into our contains method. It can be an empty array, and it can also be an array of length infinity. So for that reason, we're going to determine the time complexity with respect to our array's length, calling it n. So in our for loop here, we'll say we're iterating n times, returning true if the target comes up and false otherwise. And because we iterate n times in the for loop, this comes out to be big O of n. And you might reasonably think that why should this be big O of n? Can't it be that the target value is the first or second index in the array and you return true breaking out of the method instead of iterating n times, which is completely true and valid. But when we talk about big O, we're talking about the worst case scenario. So at worst, the target value is not in the array at all, and we have to iterate n times and reach the line where we return false. Next, we have another way of comparing two algorithms using a limit theorem. So for two algorithms, f of n and g of n, we say that the limit as n goes to infinity of f of n over g of n can tell us how to compare the two. So if this limit results in infinity, we say that f of n is big O of g of n, meaning it is either the same or slightly better. And this is a dumbed down explanation or representation of it. So I really encourage you guys to go check out the math behind it. Next, we have that if the limit goes to 0, f of n is little o of g of n, meaning f is strictly better. And you'll notice this is not big O, this is little o, which is just another way of representing time or space complexity. And finally, if this limit results in a constant value, we'll say f of n is big theta of g of n, meaning f is the same in terms of performance. Finally, to recap, we learned that asymptomatic efficiency is a way to measure performance irrespective of hardware and implementation details, We also learned about big O, little o, and big theta notation when referring to how to describe asymptomatic efficiency. And for next steps, I'd really encourage you guys to look at your past code, revisit what you've already written, and just try and identify the big O time complexity or space complexity of what you've already written. And as you progress, you'll start to realize how you can improve things from an efficiency standpoint. That's all for today, and I'll see you guys in the next one.